Welcome to the Explainer. So today we are diving into what might honestly be the next massive paradigm shift in artificial intelligence. If you've been following the AI space, you've seen models getting bigger and faster. But what's really fascinating is how they're fundamentally changing the way they perceive information. We're finally moving away from flat, rigid structures and stepping right into the dynamic, interconnected world of graph neural networks, or GNNs.
But before we get into the nuts and bolts of it all, I want to hook you with a kind of wild question. How exactly does an AI understand the shape of the universe? Just think about that for a second. We're not talking about just feeding a computer a flat picture of the night sky, right? We're talking about mapping the unseen physical laws and the vast, incredibly sparse web of dark matter holding galaxies together. By the end of this explainer, you'll see exactly how this specific AI architecture scales from microscopic molecules all the way up to the cosmic web itself.
Section 1. The shape of data beyond the grid.
Okay, let's dive right into this. To really understand why graph neural networks are such a massive breakthrough, we first have to talk about how data is actually shaped in the real world. Think about how traditional AI likes its data. It's incredibly neat, it's orderly, it's rigid. Images are just regular grids of pixels. Text is a flat, linear sequence of words. But let's be real, the real world doesn't look like a chessboard or a straight line. It turns out reality is built on messy, deeply interconnected networks. These are graphs made up of entities, which we call nodes, and the connections between them, which are the edges.
And because traditional neural networks were built for those neat little grids and sequences, they literally struggle to process these non-Euclidean, arbitrarily connected structures. I mean, if you try to force a massively complex network into a flat spreadsheet, you lose the absolute most crucial part, the topology, the relationships. That's exactly why GNNs were built. They learn directly on the graph, maintaining that essential structure. This makes them, hands down, the absolute best way to model complex systems. Whether that's atoms bonding in a molecule, friends interacting on a social network, or entire galaxies clustering in deep space.
Section 2. Passing the message. How GNNs actually learn.
So how do they actually pull this off? Let's peel back the hood a bit. Think of it kind of like passing notes in class. In a GNN, information propagates iteratively between the nodes. Basically, each node updates its own state based on the features of its neighbors. It is quite literally a message-passing scheme, almost like little envelopes of data traveling along those relationship edges.
Let's walk through exactly how this happens mathematically. It's a remarkably clean three-step schema. Step 1. For every single node in the graph, we gather up all the messages from its neighboring nodes. Step 2. We aggregate those messages together using a specific function. Usually something super simple, like taking a sum or an average. And finally, step 3. We pass those pooled messages through an update function. This is usually a learned neural network layer, often throwing in a nonlinearity like a ReLU function. Now, when you do this across several layers, something magical happens. A node doesn't just know about its immediate neighbors anymore, it builds up a multi-hop expanded understanding of the entire neighborhood.
And, this brings us to a massive advantage. By sampling these neighborhoods and aggregating the feature information, the AI can predict the broader context of the graph without ever having to flatten the data. It just naturally incorporates both the node features and the overall structural topology. This is a huge deal because it seriously reduces the need for human engineers to manually handcraft features. Plus, it helps the model generalize so much better even when labeled data is incredibly scarce. We're talking about saving thousands of hours of manual coding here.
Moving on to Section 3. A new kind of AI. GNNs versus traditional networks.
To really cement why this is so revolutionary, let's set up a head-to-head comparison. First up, we've got GNNs versus MLPs, or multi-layer perceptrons. Now, an MLP takes in flat vectors. It engages in this very rigid thinking with exactly zero relational modeling natively built in. Feature interaction only happens with local input features. But a GNN? It takes in nodes and edges, natively encoding those relationships right from the start. Plus, and this is key, GNNs share their parameters across all nodes and layers. That is a fantastic way to reduce overfitting compared to a standard MLP that only shares weights across its layers.
Next, let's look at GNNs versus CNNs, the convolutional neural networks that completely revolutionize computer vision. The crucial point here is exactly how they connect. CNNs are pretty much stuck on regular pixel grids. They rely on fixed-size spatial adjacency. But GNNs, they handle variable size, completely arbitrary graphs. They rely on topological adjacency. So, while a CNN is doing convolutions over a rigid little box of pixels, a GNN is performing aggregation over dynamic, complex, and ever-changing neighbors.
Section 4. Molecules to movements. Graphs in the real world.
All right, so the math is elegant for sure, but how is this actually solving high-stakes, real-world problems today? Well, the versatility of GNNs is frankly incredible. Because they model relationships so perfectly, we use them for node classification, think labeling web pages. We use them for link prediction, which is the magic powering your friend suggestions or tracking how information diffuses, like how viral content or even fake news spreads online. Over at computer vision, they're building scene graphs to understand how objects in an image relate to each other or processing complex 3D point clouds. And in chemistry, it's a real game changer. They are completely rewriting the rules for drug discovery by predicting things like chemical solubility and toxicity with amazing accuracy. And this brilliantly illustrates why GNNs are so incredibly flexible. Consider this. On one hand, we're modeling RNA and disease association networks where atoms are nodes and the bonds are edges. On the other hand, we have an action recognition model looking at the joint skeleton of a walking ostrich or a wolf. Now, to a traditional AI model, a microscopic disease network and a video of an ostrich are two completely, totally different types of data. They require completely different programming. But to a graph neural network, they are fundamentally the exact same thing, a graph.
Because GNNs learn the underlying structural rules of these graphs, rather than just rote memorizing data points, they support what we call zero-shot generalization. This is huge. It means they can predict the properties of drugs, chemical compounds, or network behaviors that they have literally never even seen before. They outperform traditional methods simply because they understand the relational rules of the system. And that applies whether that system fits inside a tiny petri dish or spans the entire galaxy.
Which brings us to Section 5, Unlocking the Cosmic Web, AI and the Skeleton of the Universe.
Let's take everything we've just learned and zoom way, way out to the literal edges of the observable universe. Cosmologists face an ultimate challenge here. The universe isn't a neat grid. It is structured as a cosmic web, a massive, intricate skeleton made of dark matter and scattered galaxies. And the big problem is that the data we get from observing the universe is unbelievably sparse. Trying to grasp large-scale statistics and the relations between these distant galaxies, it's an absolute nightmare for traditional statistics and regular neural networks. They just simply fall short. But enter graph neural networks. Researchers are now actually training GNNs to model particle interactions inside complex cosmic simulations. And here is where it gets crazy exciting. After training the GNN on these dynamic graphs, researchers use a process called symbolic regression to distill the learned dynamics. The GNN actually extracts symbolic mathematical equations that perfectly match known physical laws, like spring laws. And incredibly, it even proposes new equations for unknown dark matter over density. It is this perfect, elegant blend of deep learning and interpretable science.
By taking raw data from a galaxy catalog and building graphs based on nearest neighbor relationships in 3D space, the GNN naturally treats galaxies as the nodes and their gravitational pulls as the edges. This setup allows the model to capture the true, localized cosmic environment. When you feed it input features like positions and velocities, the GNN drastically outperforms flat MLP models in predicting the massive unseen dark matter halos. It's pulling profound cosmological insights directly from the structure itself.
We started off with a pretty provocative question, and I think we've seen how shifting from rigid grids to dynamic, message-passing relationships allows AI to quite literally map the skeleton of the universe. From discovering new life-saving drugs down here on Earth to decoding the massive cosmic web, graph neural networks are proving that our universe is made of connections, not just isolated data points. So I'll leave you with this final thought. If GNNs can map the unseen dark matter of the cosmos just by understanding relationships, what hidden relationships in our world will they uncover next? Thanks for joining me on this explainer, and keep learning.